Welcome back, and this is a series of videos looking at the Born-Haber cycles. They're quite straightforward as long as you understand a Hess cycle. You can think of a Born-Haber cycle as just an expanded Hess cycle. So do make sure you're happy with the direction of arrows and the definitions from the energetics pack before you start this topic. So Born-Haber cycles help us to identify the energy changes involved in forming ionic compounds. Now, we can't use bond enthalpies for ionic compounds because they are not formed of individual molecules. They don't contain covalent bonds. Instead, they contain ions in a regular lattice, which are held together by strong electrostatic forces of attraction. We can, however, use lattice enthalpy. So lattice enthalpy is the energy released when 1 mole of the ionic solid is formed from its constituent gaseous ions, starting infinitely apart. Lattice enthalpies are always negative values because they are pure bond forming. There is no need to break any bonds because the gaseous ions are starting infinitely far apart. So you'll notice that lattice enthalpies are always negative values, and they tend to be quite large because you're forming an ionic solid. And ionic solids generally have quite strong bonding, so it requires a lot of energy to overcome that strong electrostatic attraction. The larger the negative value, in other words, the more exothermic the lattice enthalpy, the stronger the ionic bonds will be. Now, strong ionic bonding, which you know from your bonding packs, depends on two things. Firstly, the size of the ions, and secondly, their charge. The smaller the ions and the higher the charge, the stronger the ionic bonding, the larger the negative value of the lattice enthalpy will be. What I'd like you now to do is to pause the video and have a go at putting the following ionic compounds in order of increasingly negative lattice enthalpy. In other words, you want to go from the weakest ionic lattice to the strongest ionic lattice. So the order you should have is that KCl is less than NaCl, which is less than MgCl2, which is less than MgO. So of these, magnesium oxide has the strongest lattice, the most negative lattice enthalpy. If you remember, ions with a higher charge means you have a more exothermic delta H lattice. And obviously you've got O2 minus, which has a larger charge than Cl minus. Okay. Also, magnesium 2 plus larger than potassium or sodium. So we've got higher charges. Also remember size, so ionic radii, and obviously magnesium 2 plus ion is smaller than the sodium ion, and it's smaller than the potassium ion, and the oxygen or the oxide is smaller than the chloride. So you've got smaller ions, therefore more exothermic delta H lat. Okay, we tend to say more exothermic rather than more negative because it's very difficult when you're talking about a negative number to talk about more or less. So we talk about it being more exothermic or less exothermic. Now, we can't measure this directly because trying to obtain gaseous ions, especially gaseous ions infinitely far apart, is practically very difficult. So you'll see later on how we can calculate this using practical values, but in our Born-Haber cycle. Another way of calculating the lattice enthalpy is to use the theoretical value, which is calculated from electrostatic theory. And this takes the charge and the radii of the ions involved into account. And we'll have a talk about that later on. But the theoretical value assumes the bonding is 100% ionic. Okay, so you're using the charges and the radii of the ions, and you can assume that all the bonding is ionic. Before we go any further, we do have to understand the enthalpy changes involved and their definitions. So on page 3 you'll see a list of definitions. It's really important that you understand these and that you've learnt them. You're going to find Born-Haber cycles very difficult to do if you do not understand these definitions. So what I'd like you to do now is to pause the video and have a go at those definitions. You will find many of them in the energetics pack or in electron structure pack from the first term. So the first and the second ionization energies, relatively straightforward. The energy required to remove 1 mole of electrons from 1 mole of atoms in the gas phase. Do notice that these atoms are in the gas phase, so you'd need to turn the element into a gas if it's not already a gas. Enthalpy of atomization is the one a lot of students get very confused with, so I'd make sure you star that one and you understand that one in detail. Notice it is the energy to produce 1 mole of atoms in the gas phase from its element. So for example, it'll turn half a chlorine molecule into a chlorine gaseous atom. That is the equation for the atomization of chlorine. Please notice it is not producing 2 moles of chlorine atoms. That would be 2 times the enthalpy of atomization. Electron affinity can be thought of as the opposite of ionization energies. In other words, this time it's the energy when you add 1 mole of electrons to gaseous atoms to produce 1 mole of gaseous ions, 1 minus. Notice, unlike ionization energy, this can be either exothermic, in other words negative, or positive. Enthalpy of formation is the energy change when 1 mole of the compound is formed from its elements in their standard states under standard conditions. And again, this one can be both exo and endothermic. Last but not least, the new one we've looked at, lattice enthalpy. Notice this is always negative because it is the energy released when 1 mole of the solid lattice is formed from its constituent gaseous ions. Make sure you understand the difference between enthalpy of formation and lattice enthalpy. They both form 1 mole of the compound, but from very different starting points. So because we can't easily measure the lattice enthalpy directly, we can construct a version of a Hess cycle, which we call a Born-Haber cycle, to find the lattice enthalpy from other experimentally determined enthalpy changes. So as I said in my introduction, a Born-Haber cycle is basically just a glorified Hess cycle. So if you're happy with Hess cycles, this topic usually presents no particular challenges. So I can take the elements in their standard states and I can turn them into my ionic lattice, and that would be delta H formation. I can take the ions in their gaseous states and I can turn them into the compound, and that would be my delta H lattice. Now all I need to do is think about how I'm going to turn the elements in their standard states into the ions, and this is more than a one-step process. But once I've worked out the steps needed to turn the elements into their ions, I can then have a Hess cycle, and then I can work out my delta H lattice. So the example we're going to be looking at is sodium chloride. So the first thing is to write out an enthalpy change of formation of sodium chloride and the lattice enthalpy. So pause the video at this point and have a go at doing those 2 equations. So enthalpy of formation, well, we're taking solid sodium and half a chlorine gaseous molecule, and we're turning them into 1 mole of solid sodium chloride. The lattice enthalpy, we're doing a similar thing, but we're starting with the gaseous ions, the sodium ion and the chloride ion, and we're using them again to form 1 mole of the ionic lattice sodium chloride. So we can now write those species into our boxes. So I have sodium, solid, and half my chlorine molecule, and I'm using that to form my sodium chloride solid, and as we said before, that's delta H formation. Or I can take the sodium ions in their gaseous state and the chloride ions in their gaseous state, and I can use those to make the lattice, and that's delta H lat. Then I have this energy change. I have an energy change between the elements and the ions, and this is a multi-step process. So firstly, I'm going to look at how I would convert sodium solids into sodium 1+ gaseous ions. Well, the first thing I will need to do is I will need to atomize the sodium, because I need to turn it into sodium gaseous atoms. And the reason I need to do that first is looking back at your definitions. This enthalpy change here is the first ionization energy, but the first ionization energy requires the starting point of the atoms in the gaseous phase. So I've got to turn them into the gaseous atoms before I can do the ionization. So I've got my delta H atomization followed by my delta H ionization, and that is 1 because I'm doing the first ionization. Now for the chlorine, I want to turn half a chlorine molecule into a chloride gaseous ion. Again, I need to turn that chlorine into a gaseous atom before I can do the electron affinity, because if you look back at the definition of the electron affinity, the atoms must be in the gaseous phase before I can do that step. So again, I need to do a delta H atomization on my chlorine first before I can do my electron affinity. Now we're in a position to calculate our lattice enthalpy given the other enthalpy changes. So we have atomization, first ionization energy, another atomization, this time of chlorine, the electron affinity of chlorine, and the enthalpy of formation of sodium chloride. So now I have the names of all my enthalpy changes from formation through atomization, ionization and electron affinity, and obviously lattice enthalpy, which is what we're trying to calculate. So I can then put the symbols or the numbers onto the lines to work out the delta H lattice. Now, the Born-Haber cycles are always drawn in the same way. This is one way of drawing them, and we'll look at an enthalpy level diagram in the next video. But we're just going to put the numbers by the side of each of these energy changes. So here we have the enthalpy of formation, and that is minus 411 kilojoules per mole. Then I have the sodium being atomized, and that is plus 108. And then I have the first ionization energy of sodium, which is plus 500. I have the atomization of chlorine, and I'm just atomizing one, remember, so it's just one lot of the atomization. Then I'm doing the electron affinity, and you'll notice this time it's a negative value. Remember, electron affinity can be both positive or negative, and I can use these values to work out delta H lattice. Now, one thing you might have spotted is the direction of the arrows. So enthalpy of formation, this enthalpy change, is equal to all the other enthalpy changes added together. So my delta H formation is equal to the sum of all the others. And as long as you can remember that, you can work out anything from your Born-Haber. So the enthalpy of formation, this enthalpy change, is equal to this, plus this, plus this, plus this, plus this. And we can see that at the bottom. We can rearrange these values to give us delta H lattice, which is what we're after, and we've come out with minus 776 kilojoules per mole. It's coming out as negative, which is a good sign because we know that lattice is always negative. So the enthalpy of lattice of sodium chloride is minus 776 kilojoules per mole.